Okay.
All right.
I'm going to move away.
Thank you, Robbie. And thank you, Joe, for setting everything up. Hi, everybody. I just want to talk today a little bit about some work that we've been doing out in Hawaii and actually around the world, as you see, on a topic that relates to a process that's near and dear to all of us who work on exoplanets, that is things blocking stars transiting. But in this case, it's actually what we think are the precursors or perhaps the remnants of planets during the formation process. And I will be making the connection to the planet formation process, which we know occurs in disks, and that we can actually study that gives us insight where even the most powerful instruments to date have not been able to probe. So this is a window that has been actually open for quite some time, but it has gotten wider now with the advent of space surveys. And I'll be talking about a phenomenon we sort of colloquially call dipper stars. And dipping refers to the behavior of the light curve. And as you can see, a light curve here, this is from K2, the Kepler successor mission, has been normalized. So one is basically the average flux over time. And you see that this is extremely irregular. We, of course, see these signals or analogous signals when planets transit their star, but you will see that these signals are actually far more substantial and far more irregular than an exoplanet, which transits on a very precise Keplerian period and which has a very characteristic, well-modeled shape that gives us insight about the size of the planet. In this case, these transits, although some of them may resemble in some crude way planet transit, you can see from the depth, these are tens of percent, and from the shape of these and actually irregular timing, that something else is going on. And what we're seeing is occultations of the star, but not by a planet, but actually very fine dust grains, which are able to occult large fractions of the stellar disk. These timescales can be very variable, from minutes to up to weeks or months, sometimes years in a few cases. What we see is this process of dipping is usually, but not always, associated with planets and stars in the very earliest stages of formation. And in this case, this is a star in the 10 million year old group of stars called Upper SCO, where star formation is actually ongoing. And what we think is that this material is basically a precursor to planet formation, or perhaps associated with that process. And by studying this dust, we'll be able to say something about the planet formation itself. So I'm going to talk about, again, this is a probe of planet-forming disks. I'm going to talk a little bit about the tools that we have available from the ground in space to do this. The possible mechanisms, there is more than one, which can produce this kind of variability. And of course, since I'm at Goddard, I have to talk about Tess, and with great gusto, because Tess is actually opening this window wider and enabling us to probe this phenomena. But Tess can't do everything. There are things that we can only do from the ground, at least at this point. And so I'll talk about the synergy between ground-based observations and space-based observations at the end of my presentation. So this is motivated by this plot, which I actually have to show. It's required of every exoplanet talk, I think, to show something where in the phase space of exoplanet science, we could spread planet discoveries out into something like incident flux or distance from the star, orbital period, and the size of the planet. And there are thousands of planets that we now know, as you know. And probably most of you know that partly because of the cornucopia that nature has provided, but also the fact that the methods primarily used to detect these, that is primarily transit and to a lesser extent the radial velocity surveys, these are strongly biased to planets that are close into their stars. And we find lots of them. And so Earth is shown as the blue dot, and everything interior to that is well inside an astronomical unit. So we find many planets, very diverse planets, on orbits that are a fraction of an astronomical unit, sometimes 100th of an astronomical unit, or hundreds. And then the question, of course, is how did they form there and what processes were? So they could form somewhat outside and migrate in through a protoplanetary disk, or they could have formed in situ. And this is actually one of the outstanding questions of planet formation today, is how those planets came to be and came to be there. Now, we do have powerful tools to study the precursors, that is the protoplanetary disk within which we think, pretty sure, planets are forming. And so we have the Atacama Large Millimeter or Submillimeter Array, ALMA, which can study the emission from dust around stars. And we can resolve down to the finest scales and when the array is in its largest configuration. And it's very impressive, the things that we are seeing compared to previous observations at millimeter wavelengths. And so we see structures and disks, but the key aspect here for this connection to planets that we find around main sequence, older middle-aged stars, is the little white bar in the lower right of each of those plots of the disk. And that's 10 astronomical units, that scale bar. So all the Kepler planets that I just showed, or most of the planet discoveries, represent the black part of that, well within an astronomical unit. And so we basically cannot resolve with ALMA, even at its widest configuration, the disks, the portions of the disk that correspond to where the planets are forming that we can see later on. So that connection is not direct. And the same is true for observations from the ground, where we can look in the near infrared for scattered light and also see these beautiful structures of disks. Again, we see a lot of wonderful substructure in these disks, shadows, bands, rings, arcs, gaps. But the scale at which we can probe is tens or even 100 astronomical units. And again, that's very large compared to the very close into the star where we'd like to see what's going on, where those planets are forming, presumably. The other issue that we have is that it's a surface area problem. That planet formation proceeds, we think, from very small objects, lots of them. This could be as small as a grain of dust, to planet-sized objects, and lots of intermediate stages in between. So the R squared versus R cubed effect is that as planet formation proceeds, anything which is based on emission, those planets or their precursors become invisible, because R squared becomes small as R cubed becomes large for a constant amount of mass. So we can probe, for example, spectroscopically through the spectral energy distribution in the near infrared or the thermal infrared material which is close into the star. But we're really probing, we're looking at emission, a amount of material which is strongly biased towards the smallest material. So as soon as the planets start to form and those materials start to disappear, the cross-sectional area is not enough then to produce a detectable signature. The star is very bright. The disk, if its cross-section area is very large, so of course we can detect it as an infrared excess, as you see in this spectral energy distribution. But those signatures will disappear, and particularly disappear when we arrive at a stage of planet formation, these intermediate stages for which we actually know really little about. We could speculate about pebbles and planetesimals and protoplanets, but we've never seen these. We have very little observational constraints on those. So these are the sort of two sides to this. And we can use a third way, which is very old and dates to well before planets were found or transiting planets were found, but is in part inspired by the techniques that we use to discover transiting planets around other stars. And that is to use occultations. So here you have a plot of, it sums this up, where you have imaging methods like ALMA and these other interferometers and the direct imaging, which can probe again into 100 astronomical units and 10 astronomical units. And again, spectroscopy, which can probe in close, but of course requires emitting area, compared to the confirmed planet distribution, which is much closer in. And by using occultation of material that's orbiting the star in the same time scale as the Keplerian period of the planets that we presume formed from that material, we have a sort of temporal window into how the disk or the material around the stars at these early stages is behaving. So occultation, using techniques from the ground and also particularly from space, the same space telescopes like Tess and Kepler and K2, probe the same sort of region of the disk where we think the planets will be forming or at least migrating to. The other thing in terms of the emitting area is just the simple fact of, again, this R squared. I'm going to try to move this. So if we go to a transiting planet, like a giant planet that is occulting the star, we get a signal about 1%. If we go to a rocky planet, of course, that signal is much smaller. Around the solar type star, at least, it's 1% of 1%. So very, very small, but still doable, at least from space. If you want to look at the precursors, then you have the problem that the occultation is 10 to the minus 6 or even smaller. However, if that material is broken up into finer particles, then basically you can see, even with a single planetesimal, let's say 10 kilometers across, if you break that into even large dust grains, 10 microns is large, you can block and occult a significant fraction of the star. And that gives you extraordinary power of signal to noise and resolution and techniques that can come into play that are not available for these other methods. So dust has been seen occulting young stars like T-Tauri stars almost as long as we've known about T-Tauri stars and what they are. And these observations were first done for the brightest stars on the longest time scales from the ground, because that's the easy ones to do. But really, the diversity of behavior has only become apparent when we started looking at these stars and monitoring them from space. Not with Kepler K2 first, this is before that, with Corot and Spitzer. And so, for example, we look at the Christmas tree nebula, and you see 2264 in both the visible and infrared. And this large collaboration, the Weisselbar collaboration, discovered this diverse behavior, variability of stars on timescales of days to weeks, occasionally months, both in the infrared and optical. Now, there's a lot of stuff going on around stars besides occultation. You have accretion, you have flares, you have a rotational signal of the stars, star spots move back and forth. But part of this behavior was, which is sort of where the name Dipper came from, was signatures, as you can see in some of these light curves here on the upper right and the lower right, particularly of those 6, are skewed trends, very sharp, very sudden, and either periodic or sort of more stochastic, which are the sort of telltale characteristics of these occultation events, and which give rise to this dipping phenomena and the Dipper stars. So there were, in these early studies, ways to identify these and characterize them. And it was very quickly realized that this was quite a common occurrence. So maybe like 1/4 of stars in these star-forming regions or young stellar clusters are behaving in this way, at least at the detection thresholds offered by these space telescopes. What space offers you, potentially, of course, is uninterrupted observations. If you can get the telescope time from a long baseline, and of course, extraordinary photometric or even spectrophotometric sensitivity, because you don't have the interference of the Earth's atmosphere. But this really became, that field really became, the window really enlarged to a bay window, if you will, when Kepler and then K2 occurred, and we were able to observe many more stars for much longer periods of times. Kepler, of course, was looking at, out of the galactic plane, at an older population of field stars. There is at least one young cluster, and there are young stars in there. But for the most part, these are not T-Tauri-like young stars with disks. They're mostly older, as Travis Berger, who is actually a postdoctoral fellow here, very carefully characterized using the characteristics of the Kepler stars that we can get. There are, of course, anomalous events that have been ascribed to disks among these Kepler stars, not ones with planets necessarily, although they might have them, but ones where the disk is not obvious or it's very, very subdued, like a debris disk. And so you have what is euphemistically called tabby star, which has these dramatic dips over time. It's a middle-aged F-type star. And then there are a few other stars that have been found among the Kepler stars, innocuous A-type middle-aged dwarfs that don't appear to be special in any way, except they have these little dips now, not dramatic, but small, which have these non-transient exoplanet-like shapes, like a talon or a hook. And the trailing side of this light curve, this shape, departure from the standard shape, is because there's something behind that's trailing that's also occulting the star. And that would be the tail of these exocomets. And so these were some of the first sort of unambiguous signatures that exocomets can be found around other stars. So that was the Kepler field. And then, of course, when K2 happened, the lid really came off on the part of the sky that we could look at. And these 19 or 20 or so fields that we could observe included portions close to the galactic plane that you can see. Galactic plane is the solid line, wiggly line in this plot, and included actually several of the star-forming regions in clusters. And so we basically started looking at T-Tauri-like stars by the hundreds or thousands and seeing the same type of variability which was found to some extent by the Corot Spitzer surveys, but now more systematically in greater numbers and for longer intervals, 70 to 80 days, of course. And so we can see basically among some of these, particularly on the sort of lower left there, these dipping events that are stochastic or periodic or a mixture of the two, with a range of depths from tens of percents down to basically the smallest events that we can detect. So dips are caused by dust, but I actually haven't mentioned where the dust comes from, except with the bow towards the exocomets, of course. That is definitely not the only explanation out there, and there are probably other ones remaining to be discovered, but let me just take you through a few of the major ideas here. So most dipper stars that are in this kind of genre where you have dipping occurring very often on timescales of days to weeks, to depths of a few percent to tens of percent, those stars have primordial disks, protoplanetary disks, substantial. This is indicated by their infrared excess, and that's the plots. Two of those plots are shown on the left-hand side here, where you have basically infrared colors, where as you move towards a more substantial disk and more infrared excess, you move from the lower left to the upper right. So bare or naked stars are in the lower left, and full T-Tauri disks that are accreting are in the upper right. And we basically explored this phase space among the stars in these young stellar clusters and star-forming regions, and found that basically, almost invariably, when you find a dipper star, it has a disk. So the reverse is not true. Again, about a quarter or so of the stars that have disks have unambiguous dipping, at least on the time scale that we've seen, and for the interval that we've been able to monitor these. That's actually a relevant question, but this has something to do with the disks. So there's some material you can see in this cartoon from this paper from Mark Kennedy, where you have material close into the star from the disk somehow intersecting in a line of sight on a regular basis, or maybe in a much more stochastic fashion. So disks, ideally, we draw in cartoons, have nice smooth surfaces, they're maybe flared, they're axisymmetric, it certainly is probably not the case that that's what reality is. It's just that we don't have yet the means by other tools to probe at those spatial scales to see this inhomogeneity. We know there's the potential for significant instabilities in the disk, and some of those actually may relate to planet formation itself. I'll just show you here the Rossby wave instability, which is occurring where you have inflection points in the entropy, and these occurs at areas, for example, where there are changes in the viscosity of the disk, like at the edges of dead zones, where things get quiet at the midplane. And these simulations now are showing you the planar view of these instabilities developing. These basically turn into vortices, but these vortices, as I show in the sketch on the right-hand side, have three-dimensional structure as well. And so they may have material that is basically being pushed out from the midplane of the disk, and if the disk is sufficiently aligned, this material can intersect their line of sight. Of course, there's also well known from other observations that as disks come in close contact with a star that's magnetized, that has a dipole or a large-scale field, that the partially ionized gas is going to interact with that field. That magnetic pressure will divert material out of the midplane, and those accretion streams or warps are another way to produce dimming events. If, again, you are viewing the disk at a fortuitous angle, fairly edge on, but not too edge on. If you are observing it from face on, that's from the top of this diagram, you will not see anything. If you observe nothing spectacular, if you observe completely edge on, your star is obscured completely, and you won't have signal to actually view the disk. So it has to be sort of at the sweet spot. So one of the interesting things we have found actually that Dipper stars have told us is that's not the complete story. The prediction, of course, what I just told you is that we should go and look at Dipper stars. That is that 1/4 of the total disk-bearing stellar population of young clusters. Go ahead and measure the inclination of the disk. They should all be sort of close to edge on, but not totally edge on. Okay, so it should be very skewed towards the cosine eyes of basically one. So, or zero, I should say. So what you have basically is measurements with ALMA or other methods, like I said, that can actually see the overall structure shape of the disk. And you can get an inclination from that. So these are ALMA images that my former student Megan Ansdell analyzed. And you can see the inclination in degrees on the upper right of these, just 4 examples. And just looking at the left-hand side of this, you'll quickly see that that's not edge on, right? It's not even close to it. And if you do the statistics, you find that the distribution is actually roughly isotropic. There is a deficit of the edge-on objects, but that's the amount we would expect. That's the effect that we would expect from the obscuration of the central star. What we don't see is the skew towards the nearly edge-on that we would have expected. So what does that mean? Well, that combined with other observations, sort of distinct observations, suggests that there's actually an inner disk that is separate in geometry from the outer disk, and that we need to be very careful when we start to look at these inner regions, and that the outer regions may be distinct zones that are not really indicative of what's going on close to the star, which is why we need to study this very carefully when understanding planet formation. So here's a cartoon showing this kind of warp or break, where you have an inner disk that's inclined at a different angle. You could be observing this edge on, but ALMA is observing the outer disk and saying, oh no, it's face on, right? And apparently the difference in this inclination can be very substantial if we trust these results. And there's independent observations, as I said, from the fact that we see shadows on the outer disk that possibly could come from, at least it's consistent with models of, the inner disk being inclined to the outer disk. And as a result, casting shadows from the star onto the outer disk. These are things that could be resolved. And even there's indications that these shadows may be moving as the disk precesses. And again, this won't be the last explanation, potentially it comes up, but another explanation is for getting material again out of the midplane where it can intersect the line of sight is winds. And this is actually potentially becoming very exciting because winds have sort of taken off, so to speak, in terms of trying to probe and understand the dynamics of inner disks. Winds may be a way for disks to not only move material around and change their composition, but actually to drive accretion, because winds can be a sink for angular momentum, separate from the other processes like viscous dissipation that we think but are not sure occur everywhere in the disk. And if you have a dusty wind, that material which is moving with the gas can actually go and move out and block your line of sight to the observer. And one other bit of information that is a tantalizing clue that this is going on in at least some cases is that stars that are getting occulted and dimming, when you look in the near to mid-infrared, where the dust is emitting at these wavelengths, you see variation that could represent these puffs or clouds of dust that are basically being raised above the midplane, being exposed to the direct radiation from the star, intercepting it, of course, and blocking them, but also basically reprocessing that radiation in the infrared and showing up as the excess. And then, like I mentioned, star-grazing planetesimals or exocomets, whatever you want to call them, depending on what their composition is, stuff that gets very close to the star and breaks up either by the fact that it is icy and the volatiles disrupt the comet or the object, or just the tidal stresses from the star itself can do this. This happens in our solar system all the time. The most prolific comet detector is not somebody on the ground with a small telescope. It's actually NASA's, it's a SOHO, Joint ESA-NASA telescope, which has basically been staring at the sun for a long time in the ultraviolet and discovering comets as they are kicked into the star by something called the Kozai-Leadoff resonance with Jupiter, passing within a few radii, solar radii of the sun, and usually being disrupted. One object goes in this cartoon, and multiple objects go out or don't go in, don't appear at all because the object has been basically completely disrupted. And all of these processes could be taking place in parallel at once. They're not mutually exclusive because young stars with a lot of material around them that are forming planets that are gravitationally perturbing the disk could be very busy places. So you can have this zoo phenomena that is happening and other things we haven't thought about yet that is all producing these occultation events. So we have this richness of behavior, and of course we have to figure it all out. So K2 basically opened this field up, and Tess has continued that by basically providing us access to the entire sky at somewhat shorter intervals. But nevertheless, that means we can survey far more diverse types of stars, diverse ages. So for example, I'll just show a couple of highlights. This is a star which is not a T-Tauri star. It's about 130 million years old. Its disk is a debris disk. It's a very weak disk. It's not substantial at all. And yet, when Tess looked at it, we had these remarkable dips in its light curve. And when you look closer at the star, you actually discover that it's a binary. One of the fun things of analyzing this, that the left-hand side is a Tess, a schematic of a Tess image. Tess cannot resolve these stars. They're only a few arc seconds apart compared to the 20 arc second Tess pixels. And so we had to use the same technique that was sort of developed or refined by the exoplanet community of looking at very careful centroid shifts in the light on the Tess image, in the Tess images, to figure out which of the stars is actually responsible for that dimming signature. It could have been both, actually, but it turned out it was the primary and not the secondary. And actually, that's, if I go back here, that's the star which has the debris disk that we can detect at least. So there might be a connection with the debris disk, but it's not a T-TARDIS disk. This is an older object. We know that it's that old because it's actually a member of a young moving group, the AB Doradus moving group, and its rotation and its stellar activity and its lithium abundance are all consistent with that, as well as its motion through space. There's no doubt about its association with that group. And to the extent we trust that age, which is pretty good, that's how old the star is. So we have at least now this dimming or dipping event, which is going on well after the protoplanetary disk stage. And so probably telling us about the leftovers of the star. This is just showing the infrared excess. I'll skip that. What's even sort of more intriguing is that there's a periodicity, which is not the stellar rotation period, in the signal of about 1.5 days. So something was very close to the star. Maybe it was one of these planetesimals that kicked in, or a protoplanet at a period of 1.5 days. This is to be determined. Tess is not just limited to 27 days, as some of you know, because you work with the Tess data. There are two continuous viewing zones at the ecliptic pole where we can basically observe most of the time select objects. And it turns out there are dipper stars in those regions. And this is one of them. And the amazing thing about this is that we basically got this huge inventory and baseline of dimming events. Each of those plots on the left basically is 1 year, from years 1 and years 3 of the mission, and hundreds of dimming events. And I'm just showing you a rogues gallery on the right-hand side of some of these. This is like snowflakes. There are no two dips are alike. So that's a wonderful challenge and an opportunity to learn about what is actually going on here, because you can do statistics. You can look at the duration of these things in a statistical sense. You can look at the depth. You can look at the shape. You can try to see if there's evolution over the months to years of the behavior. There isn't, as far as we can tell, in this time scale. In fact, looks like it's completely random. There's a periodicity which corresponds to the stellar rotation of 1.8 days. That's this subtle sinusoidal. That's not the dimming events. Those dimming events have no periodicity as far as we can determine it at all. It's completely random. This is stochastic. And we have the statistical power to detect it if it was there. So I don't know what's going on. It's one of those events, and it's a simple light curve itself. As powerful as it is, like from Tess, can't answer that question directly. We can probably rule out some things like a warp in the disk because we would see a periodicity, which we don't. Even more intriguing about this particular star and its some of its cousins in the same star-forming region is its age. It has a T-Tauri-like disk. Again, you can do this by looking at the infrared excess and a similar type of plot that I showed you before. The red star is the dipper star there of interest, and you see it has a full disk. It's also accreting as well. We can see that spectroscopically. But this disk is old, at least to the extent that we can measure the ages and by comparing observations to theoretical models of stellar evolution, by a combination of the position on the color magnitude diagram, which you can see on the left, and the fact that we don't see lithium. It's been burned in the star already. That's a lower limit on the star. The potential range of ages, which are the sort of solid curve in this colorful plot here, goes from 50 million years on up. So this disk, if we believe the model ages, is at least 50 million years old. It's significantly older than the stars with disks that we see typically around. And it's not the only one. These are these sort of long-lived disks which are now appearing in our ken, which we have not realized before. So I've talked a lot about space. I want to make a bow towards what we can do from the ground fairly quickly, because as I said, to study these objects, we just can't look at white light curves and sort of like nephrology, interpret the shape. They say something, they lead to interesting hypotheses but they can't get at the physical and chemical composition and mechanisms that are going on. We need more information from that. We need other instruments. And these instruments, to a great extent, are available mostly only from the ground. The issue is that, of course, what has inhibited the study of these stars has been the fact that you can't continuously observe them from the ground. You have your telescope, you can look at them for part of the night, and then you're done. And if the weather is not good there, you're also done even before you start. But what has come to the fore are these global telescope networks. These are often designed to find stars or objects that get much brighter, like supernova. But we can do the same thing for stars that get much dimmer suddenly. We can observe continuously objects with these continuous global, these global telescope networks like Las Cumbres Observatory by handing off the observation from telescope to telescope. And of course, we could do all the things that we do with most telescopes, like get photometry at different wavelengths and even get spectra. So if you get observations at different wavelengths, you can see the light curve and its behavior in different passbands. So you can actually construct not only how the star is dimming, but how its color changes. And the reason why its color would change as it dims is that dust does not scatter wavelengths of light, all light with different wavelengths equally. If it's me scattering, for example, there are characteristics trends. The star will tend to get redder as it gets dimmer. And you can plot that by combining the light curves in a color versus magnitude space. And then you can compare that with models, or you would expect from the interstellar medium, which is kind of the starting point of the dust we think of dust. If you want to do more sophisticated stuff, like take spectra, and particularly if you want to go after dramatic events, then you have to be able to catch these events in real time, because nobody's going to give you the larger telescope time just to hope that an event will happen that night or that week. So what you want to do is transient. The same thing that people do for supernova or these other high energy events, gamma ray bursts, you can do for dimming stars. You can use smaller telescopes like the Assassin Network, which is designed to find supernova, to trigger events using automated robotic systems to schedule automatically larger telescopes to look at the object, or at least send out an alert to the world community to say, hey, the star is suddenly getting dimming. If there's anybody out there, please look at it. Please get a spectrum. Please get many spectra. And that's what we're also in the process of developing right now. And with spectroscopy, we can do some interesting things, some of which are also motivated by, well, originally stellar astronomy, but through the passage of time, transiting planet studies, we can use the Rossiter-McLaughlin effect, where you're occulting part of a rotating star to study the structure of the dust on the scale of the stellar disk. These young stars are rapidly rotating. The Rossiter-McLaughlin effect that we would predict to see, which are the curves here, the black curve here, is on the scale of hundreds of meters per second. You don't need precision radio velocities to find that. Just high-resolution spectra will do this. If we can study at different wavelengths, we can actually see the differential emission, not just from the continuum, but from lines. Like I mentioned, spectroscopy can probe close to the star. And if the star is getting occulted by dust, by looking at the relative brightness of lines, what we call the Lighthouse Effect, as they change as the star dims, tells you the relative position of the occulter versus the lines, or vice versa. To do some of this work again, especially if you want to work in wavelengths that important molecules interact with or absorb by, again, this may get you to have to observe from space. If you want to look at the far ultraviolet or in X-rays, where gas can readily absorb, not just dust, then you want to observe from space. And so we've been using actually the Near-Gerald's Swift telescope, which was again basically designed to catch high energy events, to look at stars and how they would change in X-rays with time due to the intervening gas and dust. And this is just a sneak preview of some work which is hopefully going to make its way into the peer-reviewed literature soon, where we're looking at a star in the southern, we looked at a star in the southern hemisphere in conjunction with Tess. This is a star that's a few million years old. It's dipping all the time. You can see this from the Tess light curve. That's just one of six, one of 3 of 6 test sectors. And then you can look at the 7-year baseline that we have with Assassin to see that the variability is ongoing all the time. And again, by observing this with LCOGT, we can get the dust. And one of the things we can get from that is the grain size of the dust, because this scattering that I mentioned, that reddening versus extinction diagram is very sensitive to the grain size distribution of the dust. By observing with Swift, which we did when Tess was looking at it, we can look at the absorption of X-rays by the intervening hydrogen column density that is associated with the dust that is producing the occultation and the optical. And then by correlating the Tess magnitude or the optical variation as observed by Tess with the hydrogen column density from the X-ray observations by Swift, and then using the size, the grain size that we get from LCO, the other missing ingredient, we can actually calculate a gas to density, gas to dust ratio, or gas to solids ratio in the material responsible for the occultation. And different predictions, the warp disk or the wind or the exocomet, those make very different predictions for that gas to dust ratio. So this is where we think the future is going, a combination of coordinated ground and space-based observations. And the future actually looks very bright for dimming stars because now we have these tools, and every year it gets better. For example, JWST, to conduct triggered observations, parallel observations, just long-term observations from the ground, as well as space-based monitoring, taking into the full capacity and potential our wonderful treasure trove of tools that we have to study the mysterious early stages of planet formation. With that, I'll take any questions. Thank you.
Thank you so much, Eric. So if anyone online wants to ask any questions, please feel free to put them in chat, or you can raise your hand and we can get your audio up. And also anyone in the room, if there's anything. Yes, I see some chat. I think that was related to something else. Let's see here. Do you mind actually turning your volume up so there's not so much feedback?
Turning up or off?
Up. Yeah, that's perfect. Vlad, do you want to go ahead?
Yes. Thanks for a very interesting talk. Yeah, I never thought about it.
Hold on 1 second, Vlad. Let me try my. Actually, we're going to go.
One's on.
And then you get Sorry, Vlad, one more time.
Okay, yes, thanks, Eric, for a very interesting talk, thought-provoking objects, honestly. So, yeah, and I was thinking about it as a person who studies those young stars. You know, that one possibility might be to distinguish between the, you know, the gas component from the dust component is those stars. It's to use the transient events. You know, those stars normally show super and mega flares. So basically, you know, and at least on a couple of occasions, the ALMA observed the variability in lines of molecular ions. So it's like HCO plus and N2H plus, and that specifies the probably the response of the gas component. It will be interesting to have those simultaneous observations on ALMA with the optical observations and X-ray observations that will clearly show the those components and their changes in response to them illuminated by the emission from flares. What do you think?
or?
I got it right here.
Okay, so yeah, so the question was basically, could we use, monitoring, parallel monitoring at longer wavelengths beyond the optical to look at the dynamics of the chemical composition of the material it's a coating, particularly perhaps in responding to the activity on the star. And yes, so the issue with doing that millimeter, of course, is there is a signal to noise issue that these observations need to sufficient signal to noise. And then there's a time monitoring requirement. So ALMA is one way, but it might not be the optimal way in terms of getting enough time. But we can go to the infrared. So we can do infrared spectroscopy at regions where, for example, CO appears, and as well as ions that have infrared lines that we can actually see with spectra from ground-based facilities. And that's one of the things we're actually doing. Even just beyond just the variation in the intensity of the line, the shape of the line actually might change with the occultation for some of the same reasons that I mentioned with the Rossiter-McLaughlin effect. But in this case, the source of the emission is not the star, it's the disk. And so we can actually do a kind of Doppler tomography of the disk, or at least that part of the disk that's responsible for the emission.
Thanks, Vlad. I think we're going to go to a question in the room real fast. Ravi, did you have a question? Yeah. If you don't mind repeating that
yes,
question.
That's right. So the question is, I mentioned these observations suggest that very strongly that there is a disconnect between the inclination of the outer disk probed by ALMA, say on tens to hundreds of AU, and the inner disk that we're seeing from the occultation events on inside an astronomical unit. And that break or that warp, one of the fun ideas, I guess, I don't know if it's unambiguously shown, is it's a giant planet or some companion that is on an inclined orbit, and those torques basically set up a precession that basically breaks the disk. So you say that would be the prediction. Plus, you would basically say that there's an occurrence rate that you could sort of put a constraint on if you need a giant planet-stellar companion. So, for better or worse, depending on how you look at this, those statistics suggest that most stars actually have this kind of break, which, if you have to rely on planets to do that, is good news for the planet people. Or it could mean that it's more complicated than that. We don't have the spectral type dependence so much because these surveys are very strongly biased towards brighter stars at this stage. So when we're able to get down to lower mass stars like the sun or below, then we'd be able to have that leverage. But right now, I don't think we have that. Thank you. Good question.
All right, Chris Stark, do you want to ask your question?
Sure. Thanks, Eric, for a wonderful talk. A couple of things. One, I'm a little confused as to what we know about the long-term variability of these features. You know, I think if they're a dust cloud, they're going to be dispersed very quickly and change shape, you know, from orbit to orbit. So I was just wondering if you could comment a little more on that. Maybe I just missed it. But the second question I had was, although the signal might be small, you'd expect if it's dust, you see signs of forward scattering right before ingress and egress. Have we observed that?
The second question, is very briefly, yes, there have been a couple cases where at least in the white light signatures of space in Kepler K2, there has been seen a little bump. We do not yet have the photometric data at multiple wavelengths or band passes to show that is indeed forward scattering. But the prediction, of course, it would look blue, right? So that is one of the things that we would like to catch for the larger events, particularly. The issue is you're competing with the background variability of the star itself, or for a variety of reasons on the same time scales. But and potentially that is detectable. going back to the question of variability and the variability, that what we don't know very much about that. We have long-term variability that comes to us from ground-based observations of the most massive star, the more massive stars, the Herbig A and B stars, so the A-type and B-type stars, more massive than the sun. But for the T-Tauri stars, this information is just coming in. We have snippets because K2 has actually looked at some of the same stars a couple of times. And of course, now Tess going back, for example, I have a student working on Taurus. We are basically observing, comparing what Tess is seeing with what Kepler is seeing. I will end with this anecdote. So what we do see is basically changes in the behavior, not just dimming, but the dimming behavior changes itself from apparently on the time scale of years. This star that I showed, I won't go back and show it, that was the 130 million year old star, which had those dramatic quasi-periodic 1.5 day dimming events. Tess discovered that, and then 2 years later, Tess was going to observe it again, as a normal mission procedure. So of course, we were prepared for that. And we had all these instruments lined up to observe the star from the ground in parallel with Tess. And of course, since Murphy's law apparently is universal, when the Tess light curve came, we got all the observations, or at least most of them. Many of them were successful. When the Tess light curves came down, I showed that dipping had stopped, at least for that sector. So there is variability in the variability, and which has implications, for example, for what fraction of stars actually are dippers. I said 25% as a number just to throw out there, but that's 25% in a given 70 day or 80 day interval. Maybe all stars like this have dimming events, and it's just that they're off 75% of the time, but only on 25%.
Awesome. Well, we're at our hour, but we'll fit in that one last question here from Travis. Do you want to go ahead?
Yes, thank you. So thank you, Eric, for the great talk. So I just wanted to ask, in this era of JWST, what are the sort of prospects? Could you speak a little bit about the prospects of potentially using JWST for these sorts of objects, given their unpredictability?
Yeah, so of course, JWST opens up this access to the infrared, both to see the thermal emission from any dust, as well as the potential for any sort of gas signatures or gas absorption. As you point out, Travis, when you're dealing with a $10 billion space telescope, the resource must be used carefully, and you can't be hunting wild dips or wild geese with this. But some of these objects are frequent enough and dependable enough as dimming stars that we can sort of bank on that they will be experiencing a dimming event over a certain time. Also, some of these stars are really quasi-periodic. It's not the majority, but many of them have a strong dimming signature which regularly occurs. And these are predictable. And so we can sort of, again, rely on that. But yeah, cycle 2 is coming. And so one of my reasons for being in this part of the country is actually to talk to some of the JWST people about what we can do.
Sounds great. Thank you.
Awesome.
Thank you.
Great. Well, we are at our hour, so I just want to thank Eric again for coming out and talking with us today. Thanks everyone for joining us online and in person. And I hope everyone has a great Thanksgiving break. And I'll go ahead and end the call now. If you do have any other questions for Eric, please feel free to get in touch with me and I can connect you. And also, I think you have some space this afternoon if anyone's on campus.